In this video, we will talk about logarithmic scales and orders of magnitude. Okay, so let's see what is a logarithmic scale. Okay, so for the quantity that vary generally in magnitude, a standard scale of measurement is not always effective, and use logarithm can make the values more manageable. So now think about this. If I have a number that is, for example, like 6 and 6,000, okay? So if we want to just show 6 and 6,000 together on a scale, so now one thing about this is we know that here, okay, for example, like this one right here, maybe this is 10 right here, then we know that 6 is somewhere around here. But one thing about this is, look at this. If I extend this to, this is 20, this is 30. But look at this. Imagine how far you have to go to get to 6,000. So it seems that it's impossible for us to just show 6 and 6,000 on the same scale, right? So therefore, in this case, well, logarithmic scale is actually make it a lot easier now. So how do we actually work with the logarithmic scale? Okay. So one thing about this is now to this one, to the logarithmic scale is kind of like on the number line that you have, we are working with the scale is kind of like 10 to the x. Okay. So what does this mean? It means that you will see that here you have 10 to the negative 2, 10 to the negative 1, 10 to the 0, 10 to the 1, 10 to the 2. So here, this is actually the pattern. The pattern is we change the power, right? From negative 2, negative 1, 0, 1, 2, 3. Okay. So in this case, you will see that what happened here is we know that 10 to the power of 0 is 1. Of course, this is 10, this is 1,000. This is, I'm sorry, this is 100, this is 1,000, this is 10,000, right? 10 to the 4th. Okay. So in this case, I know that 6 is somewhere here. And 6,000 is somewhere here. Okay. So therefore, again, it seems that it's possible to actually to manage the number this way then. However, where is the location of 6 or where is the location of 6,000? Then now, this is exactly what I would like to show you then. Okay. Okay. Let's check it out. Okay. Now, for example, the first one is if I want to paste A on this scale right here, then I have A is equal to 0.04. Okay. Then now, how do I place it on this scale? Then I could actually set up is 10 to the x equal to 0.04. So now I'm going to figure out that what is the x value. Then of course, in this case, if I want to solve for the unknown exponents, then the easy way is we take the natural log, right? Oh, in this case, I should use a common log then because the base is 10. Okay. Then, of course, we know that common log of 10 to the x just equal to x. Then, if you use your calculator, then you will find out that this common log of 0.04 is about negative 1.4. Okay. I don't want to get more detail. The reason is it's really hard for us to actually to put if we have more digits. Is actually is it is really hard for us to put it on the scale right here. Okay, so one digit is actually is good enough. So is mean that in this case right here, 0.04 is roughly about 10 raised to the power of negative 1.4. Okay. Then let's see where's A now. Okay. Now you have to understand that if this is 10 to the negative 1, then this one right here must be 10 to the negative 1.5 then, right? Then now 10 to the negative 1.4 is somewhere here. Okay. So then this is actually is my A values then. Okay, so then let's try another one. How about b equal to 6,000? Okay. Then we know that it's somewhere here, right? In between 10 to the 3 and 10 to the 4th, okay? Then let's check this out if this is the case. So I have 10 to the x equal to 6,000. Then again, we take the common log. And then we have x equal to log of 6,000. And then the calculator tell me that it is roughly about 3.8. Okay. So meaning what, 6,000 is roughly about 10 raised to the power of 3.8. Then you will see that here, this is again, we know that this one right here is 10 to the power of 3.5. Then 3.8 is roughly about here. So then this is actually is my b value then. Okay, so now it is your turn. Now go ahead and try to see if you could find the location of C and D. Okay. C is equal to 6, so 10 to the x equal to 6. And we take the common log, right? And then now, of course, we have x is roughly about 0.8, okay? Then 6 is roughly about 10 to the 0.8 then. Okay. Then, meaning here is actually is my C now. Okay, now the last one is D, right? 240,000. Wow, it's a really big numbers, huh? Okay, then I have 10 to the x equal to 240,000. Then the common log of 10 to the x equal to the common log of 240,000. And then I have x is roughly about 5.4. Okay, so again, 240,000 is about 10 to the 5.4. And then 5.4 is 10 to the 5.4 is about here. So then this is actually is my D now. Okay. So you will see that right now I could use one scale to put a point like 0.04 to 240,000. Well, nice, yeah. Okay. Okay, now the next example is actually right now I would like to find the value x, right, of the number shown on each logarithmic scale. Okay. Now you will see that to this scale right here is I would like to find out what is x that put it right here. Okay. So one thing that we know, this number right here is about 3.5. Then what we could do, we could actually set the common log of x is equal to 3.5. And of course, we know that here is the base. So we could actually rewrite this into exponential form, right? It's 10 to the power of 3.5. Then if you use your calculator, you will find out that 10 to the 3.5, okay, is about 3,162.28. So then in this case, x is equal to 3,162.28 then. Okay. Okay, so now it is your turn. Okay, so now to this one, the scale is actually natural log of x. And then we know that this number right here is about negative 2.5, right? Okay. Okay, then now we could set the natural log of x equal to negative 2.5. And then remember the natural log of x, the base is e. So I have x is e to the negative 2.5. Then your calculator will tell you that this number right here is about 0.0821. Nice, huh? Okay, so then now I would like to talk about the order of magnitude. Okay. Now, given two values of A and B, to determine how many orders of magnitude A is greater than B, then we could use this formula. The differences in orders of magnitude is equal to log of A over B. Now remember, in order to work with this formula right here, we have to make sure that A must be greater than B then. Okay. Notice when one quantity is roughly 10 times larger than others, we say it is one order of magnitude larger. Okay. So what does this mean? Okay. So let us look at a simple example here. So if I have A is equal to 100 and then B is equal to 10, okay. So therefore you will see that the difference between A and B is, again, B is 10 times smaller than A, right? Okay. So if I want to find the difference in order of magnitude, what I could do is I could set up the log of 100 over 10, okay? Then you will see that in this case, I have log of 10, and log of 10 is actually equal to 1. So therefore here, this is actually is the idea about this thing. Okay, so then now, let us look at the example number 10. I would like to find the orders of magnitude of B equal to 6,000 and C equal to 6. Okay. Then now, I would like to find the orders of magnitude. Okay. Is equal to log of, now remember the biggest number is always in the numerator. Right? Then I have log of 1,000. Then we know that 1,000 is 10 to the 3 power, right? So here is a 3. So therefore, we could actually make the conclusion that 6,000 is 3 orders of magnitude. Okay. Larger than 6. Okay, so what application is actually we are using the orders of magnitude? Actually, when we try to find a measurement of an earthquake, okay, so this is actually is the time that we are using the orders of magnitude. Then we call this a moment magnitude scale, MMS. Okay, okay. Then let us work on the last two examples related to the moment magnitude scale. Okay, moment magnitude scale for an earthquake with seismic moment S. A measurement of earthquake, earth movement, okay, the MMS values or magnitude of the earthquake is this formula right here. M equal to 2 over 3 log of S over S naught, where S naught is equal to 10 to the 6 is a baseline measurement for the seismic movement, okay? Okay, so how do we actually use this formula to help us to compare two earthquakes? The 1906 San Francisco earthquakes had a magnitude of 7.9 on the MMS scale. Later, there was an earthquake with magnitude of 6.5 that caused less damage. Okay. how many times more intense was the San Francisco earthquake than the second one? Okay, so when we try to find the kind of like which one is more intense or how many times more intense, what we need to do is we would like to compare the S value. Okay, so this is exactly what we want to do. So what I'm going to do here is I would like to find what is the S value, okay, if the magnitude is 7.9, and also what is the S value if the magnitude is 6.5. Then we will be able to compare, okay, how many times more intense than in this case, okay? Okay, so then let's see how we do this. Now, of course, the first thing that I would like to do is I am going to assign variable first, okay? So I'm going to let S of 1 be the size span moment of the San Francisco earthquake. Okay, and then of course I would like to let S2 for the second earthquake then. Okay, and now how do we find S of 1? Okay, what we need to do is we are going to use this formula. So we could set up 7.9 is, oh, maybe let me do it the other way around. So 2 over 3 log of S of 1 over S naught is equal to 7.9. Okay, and now we are going to try to find the S of 1 then. Okay, so we could have log S of 1 over S naught is equal to 3 over 2 times 7.9. Okay, okay, so maybe I should make it clear that what we need to do is we could actually multiply both sides by the reciprocal, okay, of 2 over 3. Okay, okay, then now the next step is actually we are going to solve for S of 1, right? So we know that here, okay, let me simplify this. Then this is actually is equal to 11.85. Okay, then now you will see that I will rewrite this into exponential form. So I have S of 1 over S naught is 10 to the power of 11.85. So S of 1 is 10 to the 11.85 times S naught then, right? Okay, then now let us try to find the S of 2. When M is equal to 6.5 then, okay? Okay, then to this one, I have 2 over 3 log of S of 2 over S naught is equal to 6.5, okay? And again, I would like to solve for S of 2. And then now I have log S of 2 over S naught is equal to 9.75. Then we could have S of 2 over S naught is 10 to the power of 9.75. Right? Then S of 2 is 10 to the 9.75 S naught. Okay. Okay. So then now, if I want to know the first one is how many times more intense, then what we could do is we could actually use a ratio. Okay, compare the S sub 1 to S sub 2 then. So I have 10 to the power of 11.85 S naught over S sub 2 is 10 to the power of 9.75. Okay. So then, of course, in this case, S naught cancel out, right? Then if you use your calculator, then this number is what be about 126 times. Wow. It's actually telling me that the San Francisco earthquake was 126 times more intense than the second earthquake. Okay. Okay, now, right now, of course, number 12 is a slightly different, okay? But again, think about this, how do you actually work on number 12? Then? Okay, so to number 12, I have one earthquake, has a magnitude of 4.8 on the MMS scale. If a second earthquake has 1,200 times as much energy as the first one. Now to this one right here, again, meaning what the second earthquake is actually is kind of like has more, that's mean 1,200 more times more intense, okay, than the first one. Okay. Then I would like to find the magnitude of the second earthquake. Now the hints that I gave it to you is in order to find the magnitude, S is the one that we need to find, okay? If we know S, then we will be able to find the magnitude. So therefore, the idea to this one right here is, I would like to find out that what is the S value when the magnitude is 4.8, okay? Then I use the S value of the magnitude of 4.8 multiplied to 1,200 times, right? And then use the new S value to help me to find the magnitude then. This is actually is the idea, okay? Okay, so then let's try this then. Okay, so same thing to this one, I need to assign the variable first. So I would like to let S sub 1 be the seismic moment of the first earthquake. Okay, and of course, the S sub 2 will be the second then. Okay. And then now, I would like to let M sub 2 be the MMS value of the second earthquake. Okay, so I have all the variable. Then now I could actually try to work out the problem now. As my plan, I would like to know that for the magnitude 4.8, what is the S value, right? So find S sub 1 when M is equal to 4.8. Okay. So let us set it up first. Okay, and then now I would like to solve for S sub 1, just like previous example then. Multiply both sides by 3/2. And of course, S of 1 over S naught is 10 to the power of 7.2. Then S of 1 must be 10 to the power of 7.2. Times S naught. Okay. Okay. Then now, what is S of 2? S of 2 is actually 1,200 more intense than the S of 1, right? So then I could find out that S of 2 is 1,200 times 10 to the power of 7.2 S naught. Okay. And now I'm going to use this number right here, S of 2, to help me to find M sub 2 then. So we just need to plug it into the formula, 2 over 3 log of S sub 2 over S naught, okay? And again, you will see that S naught, they cancel it out. So then I will have 2 over 3 log, common log of 1,200 times 10 to the power of 7.2. Okay, then your calculator tell you that this is about 6.9. Okay, so therefore again, we could make the conclusion that the MMS values of the second earthquake is 6.9. Okay, cool. Okay, then that's it. Okay. So again, in this lecture right here, we learn how do we actually find work with the logarithmic scale and also order of magnitude. Okay, thank you.